So this is the last lecture for chapter 25, which is a short chapter. Just kind of continues going through some of the basics of what's happening with current at the microscopic level, and then we're going to describe it all here in terms of direct current. Okay. Okay. So let's say that we have the following. Direct current. Okay. Let's say that right here is a cylinder of wire, like so. Okay, there's a cross-sectional area A associated with it. There's a length L associated with it. Okay, let's say that by definition, this right here is a region of high potential, and this is low potential. Therefore, there's an electric field passing through the wire like so. And remember that this is not an electrostatic situation. We're talking about current flowing. So then, therefore, an electric field is present here within this conducting wire. Okay, there's a potential difference here across the wire. That potential difference here is equal to V. Okay, now the conventional current itself flows down the hill from high to low potential. So right here in this direction like so is the conventional current I. Now remember, as I said in the first lecture, that the conventional current I is a flux, coulombs per second. So then therefore, where are all of the vectors associated with current? Where is the flux itself as an integral? And that's described in the following way. Okay, we define a quantity. This is referred to as current density. Current density is always denoted as a small j, and by definition, it's equal to the current I divided by the cross-sectional area A through which the current is passing. So it's measured in terms of amperes per meter squared. Okay, now let me go ahead and take the area A and move it up here to the other side of the expression. Like so. And recall that the area A could be thought of as an integral, or excuse me, as a vector. This then means that J, the current density, is also a vector quantity, such that we have basically here a dot product to give us a scalar, which is the conventional current I. Okay, now in which direction does the J vector point? Well, it always points in the same direction as that of the conventional current. So right here is the J vector, like so. And then therefore, technically speaking, this right here is a flux integral. And that flux integral is an open integral. It's not a closed surface integral like it was when talking about electric flux for Gauss's law. So then therefore, mathematically, the conventional current I, once again a flux in terms of coulombs per second, is equal to the following integral. Like so. So it's basically the multiplication of the current density and the area through which that current is flowing. Now, you're never going to encounter a problem mathematically on the AP exam or even in homework or anything like that where you actually have to set up and evaluate this integral. So don't worry about that. All that we do have to worry about, however, is this expression here for the current density. Okay, now here's what we're after in this derivation. What we're interested in calculating here is what's referred to as the drift velocity. The drift velocity is essentially the electrical equivalent of the following. Imagine standing on the side of a riverbank and you toss a piece of paper into the river, and then you measure its speed as it flows downstream. That right there is what's referred to as the drift velocity, and we're concerned here with developing an expression for the electrical equivalent. Okay? All right, now what's actually happening with the electrons themselves? Okay, well, let me draw some electrons. Like so. Okay, and these electrons are like the balls in a pinball machine, for example. And they're moving in various directions like so with individual speeds, et cetera, but in general, they're drifting from the low potential side of the wire to the high potential side of the wire. Think of the wire once again as basically a pinball machine. The bumpers in the pinball machine describe the resistance. Okay, from earlier, the resistance is equal to the resistivity multiplied by length and then divided by the area. Okay, now let's say that there's some total charge here that is contained within the wire, and the total charge here contained within the wire, I'm going to refer to it just as Q. And then what we'll do is we'll take that total amount of charge Q, and we'll then have it pass through the wire like so in some time t. Therefore, the current I is equal to that charge multiplied by time. Okay, how do we write the charge itself? What's the total amount of charge? Well, the total amount of charge is going to be equal to the charge of the electron itself multiplied by the number of electrons in the wire. I'm going to call the number of electrons in the wire capital N, and then right here is the charge of the electron itself, just E minus. And then we once again divide by time here. charge divided by time is equal to the current. So right over here off to the side, capital N is the number of electrons in the wire. Okay. Okay, now depending upon the material of the wire itself, there is a density associated with the number of electrons that are actually present. Number of electrons per unit volume. This is referred to as small n. So small n is the number of electrons per unit volume. So then therefore I'm going to rewrite the total number of electrons, capital N, in terms of the number of electrons per unit volume. We would do so in the following way. We would then take the number of electrons per unit volume multiplied by the volume of the wire, the area A times the length L, and then multiplied by the charge of the electron itself, like so. So once again, get the total amount of charge that's present here in this cylinder. And then we divide by time. Okay, now the left-hand side of the expression. The left-hand side of the expression is the current I. That's equal to the current density J, and then multiplied by the area N. Like so. And then we have the right-hand side of the expression. Like so. And now let's go ahead and cancel out the area A. Here. Here. And now, right here on the right-hand side of the expression, besides the number of electrons per unit volume and the charge of the electron, we essentially have right here a distance divided by time, L over T. That's the drift velocity, which we refer to as V sub D. So V sub D is the drift velocity, and it's just equal to that distance divided by time. So replace the L over T here with the drift velocity, and when you do, you end up with this expression here, and then take the number of electrons per unit volume and the charge of the electron and move it down to the denominator on the other side of the expression. And then therefore the drift velocity is equal to this quantity here. Okay, now because it is a velocity, it is a vector quantity, like so. So then therefore, let's go ahead and plug in the vector signs like this. But the drift velocity in this case is actually described in the electrons as they flow in this direction. That's opposite of the current density J, which by definition points in the same direction as that of the conventional current. So then therefore, in terms of the vector quantity itself, we have to give this expression a negative sign. The drift velocity is actually pointing from right to left on the diagram above. So, okay. Now you're not going to be given this expression here on the actual AP exam itself, so you're probably going to have to commit it to memory. This is a little bit tricky to memorize, and we'll just take a look at one example associated with calculating it in just a few moments. Okay, before I do, there are a couple of other things here at the microscopic level that you have to be aware of, and that's the following. Let me do some erasing. Okay, let me rewrite this for reference for later. We'll drop the vector symbol at that point. Okay, in terms of microscopic quantities, there's also another means of rewriting Ohm's law. Okay, so from earlier, Ohm's law is equal to I times R. Okay, let's rewrite this expression kind of in a more fundamental way, if you will, in terms of microscopic quantities. So how do we do that? Well, take a look at, first of all, the right-hand side of the expression. So the right-hand side of the expression here, we have the conventional current I, which is equal to J times A. So, and then we have right here the resistance, which is equal to the resistivity multiplied by the length of the wire, and then divided by the area A. The area A cancels out. So the right-hand side of the expression here of Ohm's law is this so far. Okay, what about the left-hand side of the expression? Well, this is where the kid's name comes into play. Eddie, I'm looking at you. So the kid's name in this case, V, is equal to the electric field E multiplied by the length of the wire. Okay, the length of the wire here is obviously the distance D. So let's go ahead and rewrite that then on the left-hand side of the expression. So when I do, voltage V is now E times L, like so. And then notice that the L's cancel out. Here, here. And then therefore the electric field is equal to J times rho. Remember that the electric field E, however, is a vector. In addition to that, the current density J is a vector. So this right here is the microscopic equivalent of Ohm's law written in terms of the electric field E. Sometimes you'll see this expression here, Ohm's law, not written in terms of the resistivity, but in terms of the conductivity, which was from my previous video. So in that case, let's see Ohm's law in the following way. Recall that the resistivity and the conductivity are inverses of each other. Okay, so should you encounter this on the actual AP exam itself, it would be nothing more than a plug and chug type of calculation, and we'll take a look at that with my one example. So this one example is the last example for chapter 25. Go ahead and pause the film here. I'll erase the board, and then go ahead and recopy down, or copy down rather, that problem into your notes. Okay? All right, so here's what I'm going to need for the problem before I read it to you. So current I is J times A, and then drift velocity is equal to J over N. Like so. I need these guys here to do this problem. Okay, so a copper wire is 3 millimeters in diameter, so the radius of the wire then therefore is 1.5 millimeters. That's 1.5 times 10 to the minus 3 meters. It carries a direct current I of 5 amperes. And then says, find the current density and the drift velocity. We'll assume that there's one free electron per atom. The density of copper is given to us as 9,000 kilograms per meter cubed. Now that's another rho. I'm going to distinguish it, however, from the resistivity, which does not enter into this problem, right? By writing this as rho density. The rho density is just mass over volume. This is given to us as 9 times 10 to the 3 kilograms per meter cubed. So just be careful of all the rhos that are popping around these days. Okay, so the density of copper is given as that value. And then the atomic mass of copper is given to us as the following. It's 63 or 63.5 atomic mass units. Avogadro's number equals 6.02 times 10 to the 23rd. So recall that from chemistry. Recall from chemistry that this means that there are 6.02 times 10 to the 23rd electrons in 63.5 grams of copper. So now we have here Avogadro's number. Okay, I'm going to refer to this as N. That's 6.02 times 10 to the 23rd, like so. Okay, and then the mass of the copper itself, 63.5 grams, and it's 63.5 times 10 to the minus 2 kilograms, like so. Okay, the real trick to this problem, if you will, is coming up with an expression for small n, the number of electrons per unit volume. So the number of electrons per unit volume is going to equal the total number of electrons. That's going to be Avogadro's number, and then divided by the volume. So how do you write the volume itself? Well, that's where the density comes into play. Once again, as I noted right up here, density is mass over volume. So the volume V then, therefore, is the mass, this number right here, divided by the density. Like so. And then we now have the following numbers. Okay, I'm going to move the density, by the way, up to the numerator before I do. Like so. And now I'm going to write down the actual numbers themselves so you can see exactly how this calculation works. So the number of electrons per unit volume is now going to be 6.02 times 10 to the 23rd electrons. So that's Avogadro's number. Okay, and then divided by the mass, which is going to be 63.5 times 10 to the minus 2 kilograms. And then we multiply by the density. The density is given to us as 9 times 10 to the 3rd kilograms per meter cubed. So notice how the units are going to work here. All the kilograms cancels here and here. And then you end up with electrons per meter cubed. In other words, number of electrons per unit volume. So that's really the trick to doing this problem here, is getting the value of small n. All right, so it's going to be a gigantic number, as you might imagine. So 6.02 times 10 to the 23rd, and then divide by 63.5 times 10 to the minus 2, and then multiply by 9,000. Okay, and this comes out to be about 8.53 or so. 8.53 times 10 to the 27, and this would be electrons per meter cubed. Obviously, quite a bit. Okay, then after that, the remainder of the problem is nothing more than a plug and chug. Let's just go ahead now and calculate the current density. Okay, so the current density is going to be J over N times E. Okay, we have a few other things to note here. We have, first of all, the charge of the electron itself, of course, 1.6 times 10 to the minus 19 coulombs. But then we also have the current density J. Okay, the current density J is going to be I divided by A from the top board. I divided by A from the top board, like so. And the area A is going to be a pi r squared for the area of a circle. The cylindrical area here for this wire, or the cross-sectional area for this wire for this cylinder, excuse me. All right, so pi r squared, like so. And now we just plug it in. So this is kind of this laborious calculation. And when you do end up with the number itself, the units will in fact be in terms of meters per second. All right, so let me just go ahead and calculate this thing out. So I still have small n in my calculator. So let me just go ahead and work my way through the denominator. So I'm going to multiply by the charge of the electron, like so, and then times pi. Okay, and then times the radius squared. So times 1.5 times 10 to the minus 3 squared, like so. Put all that stuff up into the numerator. Okay, and then multiply by the current I, which was given to us as 5 amps. And you end up with this tiny number, as I indicated much earlier in part 1 of today's lectures. So this is about 5.2 times 10 to the minus 4 meters per second. Notice how tiny that is. We always get this impression in our heads that the electrical current is just racing through the wires, and we tend to get that impression because we're somewhat fearful of it, and sometimes for pretty good reasons. But the actual drift velocity itself, the speed of the current, if you will, as you can see, is quite small. The individual electrons themselves, I erased that diagram from earlier, but the original electrons themselves are moving at individual speeds of like about 1 billion times bigger than this. Now, the distance that each individual electron travels is quite small before it interacts with another atom, like hitting, for example, a bumper or something like that in a pinball machine. But if I now multiply this by 1 times 10 to the 9th, the individual speeds of the individual electrons themselves is in the neighborhood of like 500,000 or so meters per second. So you're talking about, let's see, like 50 kilometers per second. Those are about the individual speeds of the individual electrons themselves, which is obviously much larger than the drift velocity. Okay? All right, so that basically completes the series of lectures for chapter 25, which is a short chapter. Chapter 26, then I'll get to next time. Chapter 26 has to go through the basics of simple circuits. Okay? Thank you very much. The shirt I'm wearing, by the way, is from a band called Boom Sorrow. See you later.